kicking off this week with a big topic, reality. As in, does a real, solid, objective, testable world exist independent of any observer, at least at the level of quantum physics? That is the level of things which make up atoms, which are what we and everything else are made of, I think. Joining us now is Professor Anton Zeilinger, the Scientific Director of the Institute of Quantum Optics and Quantum Information in Vienna, Austria. Welcome tonight, Anton.
Hi, good morning, I would say.
Yes, and good evening here. Now, Anton, we've spoken with physicists before about the idea of entanglement, which is that subatomic particles, if I'm understanding it right, can somehow influence each other, be connected, even though they can be quite some distance away from each other, and that connection can happen at faster than the speed of light. And I can sort of get my brain around that in a way, but the idea that I as an observer can influence what I'm looking at, that seems stranger to me. Can you explain it to us?
Okay, well, we have learned in quantum physics that you as an experimentalist can decide basically what to look at. I mean, this is clear. This is in everyday life also. I can decide whether I look to the left or to the right. But the point in quantum physics is that by deciding what to look at, I also decide which feature can become a reality of a system, and a feature which has not had any real value before. So my choice makes reality in a sense.
Although your choice as an experimenter is then if it was completely to do with your choice as an experimenter, wouldn't the results that we come up with again and again be different depending on who was doing the experiment?
That is an interesting point, exactly. What we can decide is we can decide which quality to measure, like, for example, where a particle is or how fast it moves. But the answer of nature is completely random. Nature is free to give the answer nature wants, and that answer is the same observed by all experimentalists.
Now, sorry, carry on, Anton.
Sorry. No, so this randomness is a strong indication of a world existing independent of us. That's important. There is a reality out there which exists independent of us, but the point is that not all features which I observe have existed before I look at them.
When we talk about subatomic particles, now that's the nature of what a quantum physicist is doing. You're studying the particles and the behavior of particles that make up atoms. Is that a good definition?
This was the definition maybe 20, 30 years ago. But what is happening now is that there are more and more people working on showing that the laws of quantum physics also apply to large objects, certainly atoms, but also molecules. And right now people work at small mechanical levers like springboards to show that they also behave quantum mechanically. So there is no limit in size.
When we're looking at the things that make up an atom, are these, at their most basic level, are they things that we could grasp if we were small enough? Or are we looking at things that aren't actually, in the end, anything that anyone can grasp at? In other words, I'm not talking about metaphorically grasp at, but a particle. They're not a particle. They're something that's vibrating.
Well, in the end, what we talk about, yes, something which is vibrating. There is no possibility for something to come completely to rest in the quantum world. And it's not only something which is vibrating. The point is that in the end, it all dissolves in fields, in probability fields, a very abstract concept. So the concept of particle also disappears in the subatomic world. It's all fields. Everything is made up of fields.
When you look now, I've tried to understand this. Say if you're looking at a particle or a field, and you're trying to observe it, and it might be that its state, as you say, in nature is random, but once we observe it, it will be either spinning in one direction or another. I've heard this phrase spin used to try and explain quantum physics before.
Right, spinning is one of the ways to talk about it. I like to make it understandable to talk about a ice skater. I don't know how popular ice skaters are down in New Zealand.
Ice skaters.
Ice skaters, yes.
Ah, yes, an ice skater, right. I thought you were talking about some kind of ice cream.
No, ice skaters. A quantum ice skater would, at the same time, be able to spin to the right and spin to the left, so be in a superposition of both possibilities. And that's the picture of the spin being in for small atomic particles, being in a superposition of both possibilities, being both at the same, and not having well-defined property before I do my observation.
But once you, as a scientist, observe that ice skater, then it's either going to be spinning one way or the other.
It's either be spinning one way or the other, or I can do a different measurement which tells me I don't see it spinning, but I know that it is spinning in a superposition of both. That's a very strange thing. Yeah.
If you're trying to get to, let me ask this question another way. What you seem to be saying is that at the quantum level, reality could be one or two or maybe more states, but it's that when we observe things, we will get a certain result, and we're not able to divorce that result from our observation.
Yes, that's a very important point. We cannot, pretend that this result is completely independent of our decision what to observe. That's the important point. In classical physics, we can do that, or in everyday life. It doesn't matter when I'm in a theater, whether I look on stage or not. The same is going on. This is not tenable in quantum physics anymore.
How is it that we can? Is it not so much that we can't prove that there is an independent reality there? It's that we can't prove that our observation of it has an impact, because we can't take ourselves out of being the observers. In other words, we can't observe ourselves observing.
Well, the point is, that's a very important question, by the way. It could be just that we are not clever enough. The point is that people have made models, very simple models. They said, okay, let's try the idea that what I observe was a feature of the system before I looked at it. Okay? For all possible observations I could make on a system. And then when you do this kind of model, you run into contradictions with experiment. That's very important. You run into contradiction with experiment. So the model that what you observe corresponds to features the system had before in a one-to-one way cannot work. That is wrong.
Have you, in your work, tried to do an experiment where you, say, trick reality into behaving as if it's not been observed? Or is it you believe that's impossible to do?
That's a very good question. In every experiment, you always have features which by necessity you don't observe, because when you observe feature one, then by necessity, for example, feature B becomes not observable in the same experiment. But if I take your answer a step further, if I not observe at all, then this is a situation which happens between observations. So between observations, the system evolves according to quantum mechanical laws only because you don't observe it. If you would observe it, it would not evolve. That's another interesting point. You can freeze a quantum system by observing it.
Yeah, I think you're bringing me towards a question, which was, if once, and going back to your ice skater analogy, if once you've observed a particle and it spins counterclockwise. From then on, anyone else who observes it, including yourself, if that same particle, if you could see it again, would always spin in that same direction once it's seen for the first time.
That is very important, right? That is extremely important because some philosophers say this is the feature which makes science on the quantum level possible. If that were not the case, then we would not know what we are talking about.
Well, yeah, because then everything would be completely random. And if everything was completely random, then how could we exist?
Exactly. That's really the point. Yeah. So this fact that after one observation the feature is defined and everybody else would agree with it is extremely important. Some people say even for doing science.
Is it possible that when we're not looking at a particle, it could behave differently? And I'm going to use an analogy. There's
go ahead.
An analogy of, I don't know if you, because you're a fan of The Hitchhiker's Guide to the Galaxy, aren't you?
Yes. I'm 42 is my favorite number.
Why that doesn't surprise it doesn't surprise me at all. About the time that was made, I was living in Britain, and there was this great ad. It was a television ad for some kind of snack, and there was somebody at the zoo, and he was sitting with his back to the panda enclosure, and when he was having his snack, the pandas would get out of the enclosure and they would dance and they would jump around, and every time this person turned to look at the enclosure, they would be back in the hide. So this person concluded there were no pandas there. But every time he had his back turned to the pandas, they are out doing merry dance. Can we be sure that particles aren't doing what those pandas are doing?
Well, that's another question which has been discussed in science. And there was actually a nice picture proposed just for the fun of it, but also to drive the point home, by John Archibald Wheeler, a famous American physicist. He was the last person to have worked with Einstein. And Wheeler talked about the Great Smoky Dragon. So between the observations where we fix the quantum system, it's a great smoky dragon which evolves, but we can't see the smoky dragon. We only can see have the observations in between. Well, I would say if anyone puts up in more serious terms a model where something strange happens in between, then I would say, okay, I'm willing to listen, but I want you to then make me some prediction. Because that is what science is all about. Something which happens because of your model and which we haven't thought of yet. If that happens, then fine. I'm happy to accept your panda hopping around model or your great smoky dragon model or whatsoever. But there must be some observational consequence.
Because the thing is that even though what we're talking about might seem fantastic to a lot of people listening, I'm sure, and it seems fantastic to me, nevertheless, you can predict things. You've predicted things like entanglement, and I think in your own experiments you've proven that happens. And this is following the laws of quantum physics, which what we've been talking about describes.
Well, that's exactly the point. I mean, the whole thing can be described in a mathematically beautiful way, and I would like to stress one point. It is not at all esoteric or mystical or whatsoever. It's clear science. It's just that it runs against our usual intuition in a very, very, very strange way. And an important point is that these things can be used in technology. It's not just playing around for our interest. A lot of our technology depends on quantum phenomena like the laser or the microchips and so on and so on.
If we didn't understand these theories, well, at least if these theories were wrong, there were things we wouldn't be able to do with transistors and lasers and things like that with computers.
That's right. Or let's put it that way. If probably quantum mechanics is not wrong, but it probably, like always in science, there is a step beyond. The question is, how does science go on from here? And my personal feeling is, if it goes on, then only in a way that the present observations are all correct, plus the new theory is probably more counterintuitive than the present one, so it will be more fun actually in the future.
You're listening to Nights on Radio New Zealand National. I'm talking to Professor Anton Zeilinger from the Institute of Quantum Optics and Quantum Information in Vienna about reality. What's your attitude towards... We've been talking about this at the quantum level, so this is the level of atoms and below, smaller. But how does this actually impact on our everyday lives, apart from using this to create technology, these theories to create technology which is useful to us? But if I stare at a chair, or if I stare at my water bottle or anything else, my microphone, am I doing anything at a quantum level by just looking at those things?
No, not at the quantum level, because what we have is that for large bodies, deterministic laws are very, very precise, because quantum mechanics makes excellent predictions for the behavior of an ensemble of many, 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 many particles. So therefore, a chair and the table or whatever you call it behaves classically in the usual way. But people, as I said, are working on extending the region of quantum mechanics to larger objects, and who knows what will happen in the future.
There must be a boundary somewhere between where the world works at the quantum level according to quantum theory and where it works, say, at the Einstein level of relativity or Newton physics and gravity and kinetic energy and stuff like that. There must be a boundary somewhere.
Well, that's the point. There is no boundary. Quantum mechanics says in itself that there is no boundary. In principle, any object should behave quantum mechanically. The point is that in order to behave quantum mechanically, you have to isolate your object from the environment. So, because the exchange of information between your object and the environment destroys the quantum state, and that's the challenge: to isolate large objects sufficiently from the environment such that they behave quantum mechanically. But there's no reason why this, at least in principle, should not be possible or legal to think about.
But it would be impossible, or maybe it wouldn't be, to isolate somebody like you or me from the environment. If we were completely isolated from that, we wouldn't exist. We wouldn't hold together, would we?
Sure, we need air to breathe. We need the temperature around us, and so on. So for living objects, this is probably a too wild fantasy. But for non-living objects, there is no limit in principle.
What attracted you to this kind of work, Anton?
It was quantum mechanics itself. When I was studying physics, when I learned about quantum mechanics, I asked about this question, what does it mean and so on. And my teachers at the university either didn't answer or they kind of had answers which were evading the issue. So I told myself, this is really interesting. I want to know more about it. And so I decided to work on these kind of things.
I was interested in what you said earlier, which is that you think perhaps beyond our current understanding of quantum physics, there's a deeper level of understanding which will eventually be capable of grasping, or will have the technology to be able to see it or predict it. Is it a little bit like, for example, 100 years ago we kind of understood electricity, but even if we didn't really understand atoms as well as we do now?
Well, it could be something like that. I would like there could be something beyond. It may be also something like the step from Newton's theory to Einstein's relativity theories. That you have a deeper theory of which the one which we know is a part in the limiting case of the usual observations you do.
I know when some people talk to me about quantum physics, they say, well, there you go. You see, if reality is influenced by the observer, or only the observation impacts on the reality that we see and therefore end up working with, that just goes to show that it's all in the mind, really.
That is wrong. I would not agree with that. I mean, I should not say it's wrong. Maybe the interpretation is still a matter of opinion, but it's not my opinion. It is not just in the mind. The the history of science or the history of philosophy or philosophy of science has been signified by all kinds of views between two extremes. One extreme is pure materialism. Everything is just matter, is just stuff, or pure idealism. Everything is just our ideas. I think what quantum mechanics might tell us is that we have to find a golden way in the middle. It is not just a world independent of us, but it's also not just our ideas. It's a combination of the two. In modern language, the notion of information seems to be a fundamental concept of the world, and not just the notion of matter or of objects.
Does that mean that, for example, if you're observing the world, and I'm talking about the world around us that we live and breathe and walk around in, you don't perhaps hear somebody's eyewitness account of something and immediately doubt it and say, well, that's just their reality, and I'm a quantum physicist and I know all about reality and its vagaries. You still believe in a concrete world that we all share, most of us, unless we've gone crazy.
Yes, absolutely. Absolutely. It would be wrong to take the conclusion that the real world out there is just our fantasy. As I said before, for large quantum mechanics, for large quantum numbers, for large objects, the world is very, very, very real. There's no problem about that.
Are you interested, or do you think perhaps those, and I'm thinking about and you talked about the difference between idealism and materialism, and I was thinking about perhaps Buddhist meditation and that attempt to grasp the ungraspable through meditation, and whether there's something to that which scientists like yourself are heading towards, but in a different way?
Well, I've been asked that question very often, and you might know that I actually had some dialogues with the Dalai Lama. I met him 3 times, each time for long discussions. And there seem to be some parallels, but one has to be very cautious. There are some parallels more along the lines what I outlined before, this history of idealism versus materialism, and find a middle way and something like that. To claim that by meditation one found similar laws, then, my answer was, when people say something like that, my answer was, well, if that is true, then since science is not a finished field, it's evolving, then you must be able, based on your meditation, to tell me some phenomena, some laws of physics which we have not discovered yet. And as long as you don't do that, as long as you are not able to do that, then I don't believe that you also discover the same as we discovered in science.
Well, I guess because you could say 100 and 150, maybe 200 years ago, you could say, I've got this magical power, and then scientists came along and said, well, that's electricity that you have there, and we can tell you about electricity. And then maybe somebody could come along and in the 1940s and with a small bomb blow up a city, and you would think that person has amazing powers, but actually that's just because we now understand the energy that can be released by an atom. So it's just layers, like peeling away another layer of our understanding of the world.
Right. Yes, and I would like people who claim that by meditation they found deeper answers into these layers in a scientific way. Please tell me, what didn't we discover yet? Tell me what we have to work on as scientists.
Do you have...
We have to be able to do that,
Do you yourself have any idea or any theory about, and maybe it's impossible for you to put into language that somebody like myself can understand, about what might be beyond the quantum level, which is at the frontier of what we understand at the moment? What do you think might be beyond that?
Well, nobody can answer that at the present. We're still in the... What is going on now is that people in various labs investigate the notion of reality in context with quantum mechanics and find out what are really the lessons which we learn besides the mathematical lessons. And my feeling is once we learn this, we will be able to go one step further. But the answer is not here yet. If I would answer it, would be able to answer it, then we would probably have already the new theory beyond.
You've done experiments with entanglement, and if I read correctly, you've managed to show entanglement between two is it two atoms or two subatomic particles separated, one in one island of the Canaries and one in another island of the Canaries.
These are photons. These are particles of light.
Right. And you managed to demonstrate entanglement with those.
And we were able to demonstrate that, this connection by entanglement is much faster than the speed of light on these two islands. So there is no connection in the usual way, in the non-quantum way, between the two particles possible.
2 or 3 years ago, we spoke to a physicist from the United States who was looking at perhaps the possibility of transmitting, if not something physical, at least transmitting information using that quantum idea of entanglement, that characteristic of entanglement. Do you think that's possible?
Well, this is, I would say, if I understand right what you just said, this is a quantum teleportation.
Yes.
Quantum teleportation, you can transfer the quantum state, which is the information carried by a system, over to another quantum system, in principle, located at any distance far away. So this has been shown by various groups. That works.
If we can harness that understanding, will that eventually make it possible for us to communicate instantaneously across great distances?
Well, the point is, that is a typical answer which I have to ask with, a question I have to ask with yes and no. Yes, in the sense that the state of a quantum system is immediately influenced, and the information you want to send arises immediately at a new location. But the answer is no, because it arises in an encoded way, in an encrypted way, which the recipient cannot read. And in order to read the information, the recipient needs also a classical message, which can only come with the speed of light. So that's interesting. So there are things where information can be transmitted faster than the speed of light. This is not the only case, but in a way that we cannot make use of it. We cannot really signal anything faster. It sounds paradoxical, but that's the way it is.
I wanted to ask you another question, and I'm going to try and see if I can make this make sense. But we've only been looking at quantum physics, only been studying it for a generation or two or three. But the world we exist in, the cosmos we exist in, has been going on for billions of years before we started observing it at the quantum level. So I'm wondering what was happening with all those particles spinning one way or the other before we started looking at them.
That's another interesting question. One lesson we learned from quantum mechanics is that the relative time ordering of observations and evolutions and so on is not important. So our observation of the world today can actually observe the cosmos a long time ago, and what we call collapse the quantum state of the cosmos long time ago. So this is not a problem in principle.
Now, I'm not quite sure. Collapsing the quantum state, what does that mean?
Oh, this is what happens in the measurement. When what I said before, this kind of ice skater spinning in both directions. It's in a superposition of both before, and when I look, it's only either. And this is what we call the collapse of the quantum state. So it could be that the universe is in a superposition of many possibilities until the observer looks at it. And the observer is you.
Right. But then that gets back to that question of whether I'm influencing the universe, me personally, but how can I be doing that when there's so many of us, billions of us, looking at the same time?
Yeah, it seems that this raises all kinds of puzzles, and that's the kind of open questions in the deep philosophical understanding, which we are not yet really able to answer.
Do you find yourself doubting the world around you much, or you're quite comfortable in the physical world despite having this understanding of the layers underneath it?
Well, I think a quantum physicist like me lives the same way life as other people. The world is real around us and so on. What kind of quantum mechanics does is probably sharpen your mental eye for possibilities, for saying, well, it's this way, but it also could be very different. And that makes maybe for a more open world view than for if you would believe in determinism and a fixed classical world.
Do you still have the boat 42?
I have my boat 42, yes, absolutely. Yeah. I love it.
Where do you go sailing in Austria? On one of the lakes?
We have beautiful lakes here, which are, I know it's nothing compared to the fjords on the southern islands, but it's my boat is on a beautiful lake which goes right into the Alps. So when you sail there, you sail between nice mountains and so on. It's not very big. It's nothing compared to anywhere else in the world, but it's big fun.
Anton, it's been fascinating talking with you. Thanks for joining us.
Okay, good evening, and maybe another time. Bye-bye.
Thank you, Anton. It's Anton Zeilinger, the Scientific Director of the Institute of Quantum Optics and Quantum Information in Vienna, Austria, talking about the nature of reality at the quantum level.